Well, hello there, everyone, and welcome back to our videos. We are now on to section 4.1. So we are now moving into some of the applications of this calculus we've been learning. So any of you out there who've been looking for more real-world connections to this math, you're about to get a heavy dose of that. Okay. So section 4.1 is over a concept that we call related rates. And the idea here is we've been talking about derivatives as rates of change. So now we're going to look at rates of change that are related, or maybe looking at in a problem we have more than one rate of change. And if we know one or two of them, how do we find the other one? Okay. Before we get into that, though, I want to go back to implicit differentiation. And in chapter 3, we learned that if we have a problem like this, something like x to the fourth equals y squared times x squared, we can find dy dx, okay, so the derivative of y with respect to x, by using implicit differentiation, right? Now, notice in that case, we're taking the derivative of y with respect to x. We didn't really talk about this, but we could have found dx dy, and in that case that's an example of where we think of x as our output variable and y as our input variable. Okay, and so in that case we would actually do that very similar to the way that we find dy dx, except for now because x is the output variable, when we take the derivative of the x terms, like say x to the fourth, we have to multiply by dx dy since that's the output variable. And when we take something, the derivative of something like y squared, we just leave that as 2y. Don't have to do that extra derivative now since that's our input variable. Okay, but we don't have to stop there. So notice here the directions say take the derivative of the following function with respect to t. Now notice there are no t's here in the function, right? And so what we're going to do is assume, because we don't see t here, that t, or that both x and y here are going to be implicit functions of t, which means there are some formulas out there. Again, we may not know what they are, but x, we can write some formula so that x is a function of t and y is a function of t. And when we do that, then we can still take the derivative of this function with respect to t. We just treat it as if it's the input variable, even though it doesn't appear. So here's what that would look like. So here on the left-hand side, I've got this x to the fourth. So I'll take the derivative there, which will give me 4x cubed. But then I'm assuming, as I wrote over here on the left, that x is a function of t. And so using the chain rule, we'd have to multiply by the derivative of that function, which would be dx dt, since x would be our output variable and t would be our input. Then we go and do a similar thing on the right-hand side. So now we're going to take this derivative of y squared x squared with respect to t. Notice again, we don't see any t's there, but what we do see are two functions being multiplied, right? So the y squared times the x squared. And when we see two functions being multiplied like this, how do we find the derivative? We use our good friend, the product rule, right? So we'll take the first, y squared, times the derivative of the second, which is going to be 2x, but again, we're taking the derivative with respect to t, this variable we don't see here. So we have dx dt by the chain rule, plus, and I'm sorry, I'm going to have to go on a second line here, the second function, so that x squared, times the derivative of the first, the y squared, which is 2y, and then again, we're taking with respect to t here, so we get dy dt. Okay? And then we could continue on from there, finding dx dt or dy dt or whatever we're asked to do based on the information we're given. Okay, but the big takeaway I want you to get from this is that we are able to take derivatives of with respect to variables that don't necessarily appear in the problem. All right, so let's look at a more concrete and application example of this. So let's say we have a spherical balloon, which I know is a little unrealistic because balloons are not perfect spheres, but just bear with me. That's being filled with air at a constant rate of 2 cubic centimeters per second. Okay, so that tells us the rate at which the volume is changing over time. We want to know how fast is the radius increasing when the radius is 3 centimeters. So you can imagine that probably the radius on this balloon started smaller than 3 centimeters, and as the balloon expands, the radius will eventually reach 3 centimeters. And then at that moment, we want to know what is the rate of change of the length of the radius. Whew. Okay, a lot going on here. So in a problem like this, something would be super helpful just to give us a visual of what's going on. Let's draw a picture. So I'm going to draw my best effort at a sphere here. Okay, so it's supposed to be a sphere. And since it mentions it in the problem, I'm going to go ahead and draw a radius here. I'll call that R. That will be the radius. Okay. And then we're also talking about the radius being filled with air, which, as I mentioned, has to do with what property of this sphere? That's right, the volume. So some information that might be helpful here would be to write down the volume equation. So that would be V equals 4/3 pi r cubed. And it's okay if you don't remember that. That is the formula for the volume of a cube, or sorry, a sphere. Okay. And again, we're trying to figure out how fast the radius is increasing at a certain point, right? We want to know how fast the radius is increasing when the radius is 3 centimeters. So let's try to write this in terms of derivatives. If we're trying to find how fast the radius is increasing, well, we're looking for a change in the radius. So that might be like a dr. And then with respect to what are we looking for this change? Well, probably because the balloon is being filled with air over time, we're trying to find it with respect to t. So what we're looking for here is what would be dr dt. Okay, and that's supposed to be an r, not a v. Okay, so we have to somehow find that. And the only information we have is this formula for the volume of a sphere. We've also got this thing about how the amount of air in the balloon is changing, and then we're looking for when the radius is 3 centimeters. So, how are we going to do this? Well, what have we been doing for a lot of this quarter? Oh, right, taking derivatives. So maybe we should do that here. Also, notice that in our volume formula here, we have two variables, right? A v and an r. And you might wonder which one of those are we going to take the derivative with respect to. Well, no, I just erased it, but we decided we were trying to find dr dt, so the derivative of r with respect to time, or with respect to a variable t. So what do you suppose we're going to do to take the derivative here? Right, we're going to take it with respect to t, which means we're going to do some implicit differentiation. Woohoo! All right, here we go. So when we do implicit differentiation, let's start on the left-hand side. So take the derivative of that v there. So that's just a single variable, so that's going to be a 1 times, and then we're taking the derivative with respect to time. So this is going to be d capital V dt equals, over here, notice that this 4/3 and pi, those are just constants, right? Those are just numbers. So we can leave those out front. Times, now we take the derivative of this r cubed, which is going to be 3r squared. And then again, we're taking with respect to time, so dr dt, which is good because we said that's what we're looking for. Okay, now doing some cleanup here. On the left, I have the 1 times dv dt, so that's just going to give me dv dt. Over here on the right-hand side, we have a 4/3 times pi times 3. I'm going to leave the pi as is for right now, but if I do 4/3 times 3, hopefully you notice these 3's cancel. So we just end up with 4 pi r squared times dr dt. Okay. All right, and again, we're trying to find dr dt, which means we probably want to isolate it. But before we do that, let's see if we can fill in some of these values that we have in this problem. So let's start with the dv dt here. Is there something we can plug in for that somewhere? Well, what does that mean? dv means a change in the volume over dt, meaning with respect to time. So do we have some information about the change in the volume with respect to time? Oh yeah, right here, right? This 2 cubic centimeters per second is telling us how the volume is changing. So therefore, we can replace that value there. So that would become, that become 2 equals, we have the 4 times pi, and then we have this variable r. Do we have some information for that? Oh, right, yeah, because we want to know when the radius, what the dr dt is when the radius is 3, so we can plug that in. So that'd be 3 squared. Sorry, I changed colors there. And then we still have the times dr dt from over here. Okay, and now notice in this equation, the dr dt here is the only thing that we don't have a value for. So we can rewrite this, first of all, as 2 equals 3 times 3 is 9 times 4, so we have 36 pi times dr dt. And then we can isolate the dr dt by dividing by 36 pi on both sides. And when we do that, again, I apologize, it's not quite enough room on here. Hopefully you see that what we end up with is dr dt equals 2 over 36 pi, which I think that can reduce to 1 over 18 pi, which if I plug that in the calculator, it looks like I get something like 0.018. Okay. So good, we found that rate of change. Now, in order for this to make sense, especially in the context of the problem we're working on here, we need to include some units. And how are we going to find those units? Well, we can use what's in our derivative to figure that out. So here we have a dr over a dt. So what are the units for the r? Well, that's the radius, which we measure in centimeters. And then the t, that's for time, which the only time units we're given here are seconds. So it looks like our rate of change of our radius is 0.08018 centimeters per second. Okay? Now, to put that in context again, what does that mean? Well, it means at the moment when the radius of the sphere, and I'll draw the sphere back in here, is 3 centimeters as it's filling up, the length of the radius is changing at a rate of 0.018 centimeters per second. Now you may be asking, well, shouldn't it always be changing at that rate? And the answer is no, because think about as the balloon is increasing, or as the size of the balloon is increasing, right? You think about it kind of filling up in all different directions at different volumes. The radius will be different, so the length of that radius will be changing at different rates. Okay, even though the balloon itself is being filled with air at a constant rate, the radius will be changing at different rates. All right, let's do another one because that was just too much fun. But before we do that, first thing I'll tell you is with these related rate problems, this is not one of those things where I can tell you how to do it every single time. Okay, this isn't like the power rule where you see a power function, use the power rule to find the derivative. These problems don't work this way. But what I can give you is a framework with which to approach these problems. So, or a problem solving strategy. So when you're trying to solve a related rates problem, here is kind of a process you can follow. First, assign symbols to all variables, and involved in the problem, and a very important step you saw that we just did, draw a figure if applicable. And in fact, I would say do that first if you can. Draw a picture and then label some things with variables. Next thing, state in terms of the variables the information that is given and the rate you're looking for. Okay, very important. This is a way to organize yourself and say, what information do I have and what information am I trying to find? Then the third step, find an equation that relates those variables. So in the last one, we kind of skipped that second step, but we went to that third step where we had an equation that related volume and radius. So we could use that to solve. And then as it says, using the chain rule, differentiate both sides. And I would maybe even expand on that and say, using the chain rule and implicit differentiation, differentiate both sides. And then substitute all the known values into your equation and solve for that rate of change you want to know. Okay, so let's look at another example here. So we have two airplanes that are flying in the air at the same height. The first one, airplane A, is flying east at 250 miles an hour, and airplane B is flying north at 300 miles per hour. And they're both heading to the same airport, which is located 30 miles east of airplane A and 40 miles north of airplane B. And they want us to figure out at what rate is the distance between the airplanes changing. Okay, so let's take a look at this. First thing I'm going to do is draw in my planes. And let's see, one is flying east and one is flying north. So I'm going to have the first plane here. And I apologize, or maybe I don't. That's the best I can do. And then the other plane will be here. Okay, and again, this one down here is going north. This one down here is going east. And they're both approaching the same airport. So I use this point AP for airport. This is plane A, this is plane B. We're told that airplane A is 30 miles, or the airport is 30 miles east of airplane A, and it's 40 miles north of airplane B. And then we're looking at something about the distance between the airplanes, so we probably want to mark that in there as well, so we get this. Okay? So this is our diagram, and hopefully you noticed something about this diagram, right? What kind of shape have we just formed here? Yeah, we've formed a right triangle, right? And we also want to introduce some variables, and we know with right triangles, something we like to do is label the sides using particular variables. So I'm going to call this side here, since it's due with airplane A, lowercase a, this one here, lowercase b, and then this one here, lowercase c. All right. And so that's our first step. So we've put some, we've drawn a picture, we've labeled some things with variables. Oh, and the other thing we need to do is identify some rates, or a rate we're trying to find. And notice again up here, they want us to find the rate at which the distance between the airplanes is changing. Well, what represents the distance between the airplanes here? Well, that would be side C, right? And so it would be a rate that describes how that's changing. Well, that would be dc, so a change in c with respect to what? Well, up here I see some stuff that are miles per hour, which are distances changing with respect to time, so probably we want to find dc dt somehow, right? Because I don't know the rate at which that distance between them is changing. Okay, so now we can move on to step 2. So do we have some sort of an equation that will relate these three values, this a, this b, and the c? Oh yeah, right. This is a right triangle, so something we know will relate those three things is that good old formula a squared plus b squared equals c squared, which is, oh right, the Pythagorean theorem. Okay? So now what? Well, again, we're trying to find a rate of change, so we should differentiate. So we'll take the derivative here. So if we do that with the a, we'll have 2a, and then we're finding derivatives with respect to t here, so we'll have to multiply by dA dt. Plus, for b squared, we do the same thing, 2b times dB dt. And then for the c, 2c times dc dt. Okay, and notice in the problem here, we have the values for a and b, right? So we could plug those in. Do we know the value for c? Well, we don't know it, but could we find it? Hopefully you're nodding your head and saying yes, right? Because we have a right triangle, we know two sides of the right triangle. We can use the Pythagorean theorem to find the missing side. For now, I'm going to skip that step and just tell you the length of this missing side is 50 miles. Okay, so we know A, B, and C. We're trying to find dc dt, which means we should probably still also look for dB dt and dA dt. Now, do we know those values? Well, dA dt, what does that mean? So it's the change in A with respect to time. So the change in this length with respect to time. Do we have any information about that? Oh, right here, right? We're told that that distance is changed and the plane is flying at a rate of 250 miles per hour. So that's probably our dA dt. And similarly, dB dt is going to be the rate at which this side is changing, which is going to be 300 miles per hour. So with all that information, we can go ahead and plug in our values. So we'll have 2 times 30 times the value for dA dt, which is, what was that again? Oh yeah, 250 plus 2 times the value for B, which is 40, times dP dt, which is 300, equals, and darn it, of course, again, I ran out of room, and this is probably hard to read anyways. So 2 times 40 times 300 equals, and I apologize, I have to go on the next line, 2 times 40, 2 times 50 times dc dt. Okay? So notice we can work this out, add those together, and multiply this out, and divide. And I'm going to skip those steps for now. And if you do that, what we will get is that dc dt, so the rate of change of the length c with respect to time, is 390. And what will our units be there? Well, again, it's a change in c with respect to time. The units on c are miles. Doesn't say miles. And great, just erased that. Perfect. Just what I wanted to do. Okay, so the units on c are miles. What are the units of time we have here? Oh yeah, we see hours up here, so it'd be miles per hour. So we have the dc dt is 390 miles per hour, which again, in the context of the problem, that's telling us that the rate of change, or the rate, the distance between the airplanes is changing at this particular point is 390 miles per hour. So it is decreasing in the rate that it would go down by 390 miles each hour. Okay? Good times. I'm going to leave it there for now. We'll be back later with more fun with these related rate problems. Thanks for watching.